Here we have a uniform magnetic flux density field that is only in the z direction. Here we have a positive charge q and it's moving with some velocity u. Let that velocity be in the plane of the page. We know the force the charge will experience is QU cross B, so the direction of the force will be perpendicular to both the velocity and the magnetic flux density field. Since the force will always be perpendicular to the velocity, the charged particle will move in a circle. The magnitude of the force is going to equal QU times B, and the force is also equal to the mass times the acceleration. When something is moving in a circle, the acceleration is the velocity squared over the radius. Solving for r, we find that the radius of this circle is given by the mass times the velocity over the charge times the magnetic flux density field. This observation of our charged particle moving in a circle is an experimental verification of this fundamental equation. This is also the basis for mass spectrometry. Let's say we want to identify whether we have silicon or arsenic. So if we could produce ions of the silicon and arsenic, what we would then do is we would apply a voltage and accelerate those ions by the electric field between our source and a metal plate here. Now, if the metal plate has an opening in it, those ions will proceed into a region where we have a magnetic flux density field. Now, once in that region, the force due to QU cross B will have them move in a circular motion. The radius of this circle is given by mu over QB. So if we know the velocity, the charge, and the magnetic field from a measurement of the radius, we can determine the mass of the particle. Here are the masses for silicon and arsenic, and if the ions are singly ionized, they have a charge of plus 1.6 times 10 to the minus 19 coulombs. The potential difference between the source of the ions and the magnetic field region is V, so the kinetic energy with which the ions are going to enter the magnetic field region is Q times V. Or the charge on our ions, 1.6 times 10 to the minus 19th coulombs, times our potential of 100 volts or 100 joules per coulomb. So the kinetic energy is 1.6 times 10 to the minus 17 joules, which equals 1/2 the mass times the velocity squared. So we can calculate the velocity for the silicon and arsenic ions by substituting in the mass here for the silicon and arsenic ions. So if our species is silicon, it will enter the magnetic field region with a velocity of 2.62 times 10 to the 4th meters per second. And if it is arsenic, it will enter the region with a velocity of 1.6 times 10 to the 4th meters per second. With the magnetic flux density field inside our spectrometer being 0.1 Webers per meter squared, we can then calculate the radius of the circular orbits. If the species is silicon, the radius will be 7.6 centimeters, and if the species is arsenic, the radius will be 12 centimeters. So if the distance between where the species enters the magnetic field region and hits the screen is 24 centimeters, we know the species was arsenic. And if the distance is 15.2 centimeters, we know that the species was silicon.